Hello, in this video I'm going to continue with the topic of simple machines, this time looking at the inclined plane. This is one of our 6 simple machines. It might not sound like much of a machine, but remember that what we mean when we use the word machine is some device which can make things easier for us in the world. It can give us more advantageous outcomes when we're applying our understanding of physics to the world. So, how does an inclined plane work? So say we want to, first of all, we're going to look at an ideal inclined plane. So this is one which doesn't have friction. That just, creates a few problems if we add friction in, and we're just getting started. So we'll bring friction in later on. So we've got some weight sitting here on the floor. And say we're able to deadlift, I don't know, 100 kilograms. So we're capable of lifting, if we take G as 10 with 100 kilograms, 1,000 newtons. So let's say this is 200 kilograms. So we would need, if we were going to lift this up, we would need to apply about 2,000 newtons in order to lift up this weight. And say we wanted to lift it through some height h. Well, we've got a problem because we can only lift up half of that. So this is where the inclined plane can help. Now, if we change this situation to having our slope instead, our inclined plane at some angle, and we now have our 200 kilograms at the bottom of the slope, we can pull it up the slope instead of lifting it straight up. Now, if the length of the slope is d, we can use our work principle. Work in is work out, because this is without friction. We've got no losses going on here. This is an ideal plane. And we've got some F here, our input force. So F input multiplied by d, the length of the plane, that's the amount of work we're actually going to be doing, will be exactly the same as lifting up this force of 2,000 newtons multiplied by h. So these things have to be equivalent because of conservation of energy. Well, we know that d is greater than h, so our F input is going to be greatly reduced. So that's what we're looking at here. Remember our other descriptions that we had. We have our mechanical advantage. So what is the multiplier of force that we're going to be getting here? So our output equivalent force is we're lifting upwards with a force of 2,000 newtons. But our input force is going to be much less than that. And that is also going to be equal to our velocity ratio in the ideal case. Remember, when we've got no losses and we're 100% efficient, the mechanical advantage is equal to the velocity ratio. And the velocity ratio is d over h. So the distance that we move our input force through divided by the distance that our output force has moved through. So these things are equivalent to each other. So our mechanical advantage that we're getting from an inclined plane is a geometric property of the plane, because d over h, this is d is our hypotenuse, h is our opposite when we're looking at theta. We just turn this into a little triangle here with a theta. We've got a right angle triangle, that is our h, that is our d. So sine theta is h over d. So this is, our velocity ratio is 1 over sine theta. And of course, our velocity ratio is equal to our mechanical advantage. So in this case, we know that we're capable of lifting 1,000 newtons. That's what we're doing in the gym when we're doing our deadlifts. So if we can lift 1,000 newtons, we want a mechanical advantage of 2. So if we're aiming for a mechanical advantage of 2, and see, this is how we're putting what we need in the world. We're not looking for a description of the world here. This is engineering. This is our target. that we've got here. This is our target, a mechanical advantage of 2, in order to lift this thing based on what we know we can do as an input force. So if we want a mechanical advantage of 2, therefore we need sine theta, the angle of inclination of the plane, has got to be equal to 1/2. So we're going to have to set that to 30 degrees, our slope. If we've got a 30-degree slope, we've got a mechanical advantage of 2. So see how this process is so different to what we've been doing in pure physics. We're not just saying, oh, some slope has turned up. What are we going to be able to do on this slope? Yeah, you want to start thinking as an engineer of, well, what force do we have available to us? And if we've got a particular force available to us and we want to achieve a certain task, as in lift 2000 newtons, then that gives us our mechanical advantage, that's our target, and that sets our angle on the slope. So this is engineering thinking rather than physics thinking. So it's a completely different way of going about this. But you can see this is just a geometrical property of the slope, and that's without friction. So now let's move on to a more real world case of, well, what happens if we do introduce friction into all of this analysis? Okay, the first thing we're going to do moving into friction here on inclined planes is look at a thing called the angle of repose. Now, the angle of repose we're going to denote using the Greek letter phi, and this is the angle of the slope that brings an object into limiting equilibrium. So let's put that on a picture just to make it a bit clearer. We got some slope here, we got a block sitting on it. The angle that the slope is at, the inclination of the slope, we keep on increasing it until the block starts to slide down the slope. So on the point of the block slipping at that limiting equilibrium, we've now got a setup with our 3 forces of weight, reaction force. Friction will be acting up the slope because it's opposing the motion down the slope. And at that limiting equilibrium, the angle of the slope is phi, the angle of repose. Right, so let's just do a little bit of basic mechanics on all of this. Our friction is equal to mu r, where mu is the coefficient of friction. We can then resolve perpendicular and parallel to the slope. So r is going to be equal to w cos phi, and the friction at the point of limiting equilibrium is going to be equal to w sine phi. Now we can just rearrange the top one to say that the friction divided by r is equal to mu, and then we can take the bottom two, divide the lower one by the upper one, and say, well, friction divided by r is equal to w sine phi divided by w cos phi, so that is equal to tan phi. So we've now got this relationship between the coefficient of friction, mu, which is equal to the tan of the angle of repose. So this is our finding here. We've got a link between angle and friction, which is what you'd expect, obviously. You know, the greater you're going to lift up the angle, the more you incline the slope before things slip, well, you must have greater friction in order to hold things in place. Right, so we're going to use this in our analysis of planes with friction. So let's take this over here, make a note of the finding that we had, which is that mu is equal to tan phi, and then we can return to the example that we had earlier on, but add friction in. So we've got our slope, which is at some angle theta now, so we're not putting it at the angle of repose. That will just turn up later on. And we've got our block in it. We've got the weight going down, which is we're going to say is equal to mg. We've got an input force, which is what we're using to drag the object up the slope. We've got our reaction force, as usual, perpendicular to the slope. We've got the friction opposing the motion, f lowercase r. And the length of our slope is d, and it's going through a height h, because this is what we're comparing to just having our mg going through, this is our f out, through a height of h. Instead, we're going through a distance, full distance of d. So these, remember, that was our comparison when we were looking at our conservation of energy. So let's start then. That's all of our setup. Let's start off with our conservation of energy. So for conservation of energy, we've got the change in our potential energy, or the work done in raising the mass. So we could say either way on that, the F out times H, so that's mgh, so force times distance. Then we've got to add on the losses that we've got, which is the friction multiplied by the length of the ramp. So again, a force times a distance. And that is going to be equal to the work that we've put in. So F in times the length of the ramp. That's our conservation of energy. We can then look at F equals mu R and say that our friction is going to be equal to mu R, which is mu mg cos theta. And mg is our F out. So mu F out cos theta. We can now sub this into the top equation. So if we put 2 into 1, so that's our equation 2, that's our equation 1. We put 2 into 1. That means we're going to get, we can factorize the F out. So we got F out multiplied by H in the first term. And then we've got mu d cos theta in the second term, and that is equal to F in multiplied by d. Right, so we're now in a position where we can immediately see we can get the mechanical advantage out of all of this, because our mechanical advantage, which is F out over F in, so mechanical advantage is going to be equal to d divided by H plus mu d cos theta. Let's divide everything by the d's. So we get a 1 on top, divide every term by d. We've got H over d plus mu cos theta. Now H over d, we've already seen that before. We saw that just on the basic geometry. Remember when we drew out the geometry of the slope? We got d there, we got h there. H over d is sine of theta. So this is looking good. We got 1 divided by sine theta plus mu cos theta. So that's our mechanical advantage expressed in terms of mu and theta. But of course we can rewrite that using angle of repose if we want to. It's not necessarily better. I mean, you know, but it's easier. You can measure an angle of repose quite easily. You know, you just put a block on a slope, lift it up until it moves, measure the angle. So, okay, you can then work out what coefficient of friction is off of that. But you know, angle of repose is nice. So let's whap all of that in there and see what we end up getting. So mu is tan phi. So let's write all this out again, moving over to green to do some angle of repose on this. So we're going to have 1 divided by sine theta, and then I'm going to split out the angle of repose into sine phi over cos phi, and then cos theta. Now we can, well, let's get rid of this cos theta at the bottom here, and we can say that is cos theta, cos phi. I keep getting my thetas and phi's mixed up. Cos phi divided by sine theta cos phi plus sine phi cos theta. Really having to take care to say these Greek letters the right way around. And for those of you who are familiar with your trig, you'll see that that is one of our trig identities for multiple angle. So that's going to end up giving us cos phi divided by sine theta plus phi. And that is then our mechanical advantage in terms of angle of repose, rather than in terms of coefficient of friction. So we've got these two expressions now for mechanical advantage, but what do they actually mean? I mean, it's nice to interrogate things a little bit when you come up with a new formula. So let's poke around at these and see what we've got. So right, I'll write what we just found out here. So we've got two ways of working out mechanical advantage. We've got the angle of repose one, which was cos phi over sine theta plus phi. And then we also had the one where we were just dealing with the coefficient of friction. So that was 1 over sine theta plus mu cos theta. And now we can go back to our initial problem. We've got a slope on angle theta. So remember these ones here where we got this angle of repose, this is just a way of bringing in friction into it. It's got nothing to do with the slope, the angle that the slope is actually at. It's just a way of quantifying the friction. So we were applying 1,000 newtons, the most that we could apply to this thing up the slope, which was length d, and that was instead of applying 2,000 newtons to lift straight up through 1 meter. So that was our comparison. This is going through a distance d instead. So the engineer in us is saying, right, we've got this target mechanical advantage. Target mechanical advantage is 2. We know that that's what we need to be able to achieve. So what is the maximum mechanical advantage we can get in a particular setup with friction? Because the friction is limiting what we can do for mechanical advantage. So our MA max is going to be, well, we know we've got maximum mechanical advantage when we got the lowest possible slope, because the smaller the incline, the greater the distance we're applying our force through, and the greater the distance we apply the force through, the lower the force has to be. So that's a chain of, we reduce the angle, so the length of the slope goes up, so our force drops because we're multiplying the force by the distance. So our maximum angle is going to be when we've minimized theta in this equation here. So when that is at its smallest, so we know that that is going to be cot of the angle of repose. So that's giving us a limit on that. So say we want to get this target of 2. So 2 has to be less than cot phi. Our tan phi has to be less than 1/2. So we've got an upper limit here on what our coefficient of friction is going to be, because remember, tan phi is the coefficient of friction. So if we want, on any slope, any inclined plane, we want to get a mechanical advantage of 2, we have to keep our coefficient of friction below 1/2. So that's something that we've got immediately on this. Let's say we were going to take something near to this limiting case. So if I do inverse tan of 1/2 and then round it down. So let's say we had an angle of repose of 26 degrees. And we were going to put this now into our mechanical advantage. We want to get a mechanical advantage of 2. We've got cosine of 26 degrees over sine theta plus 26 degrees. So what sort of slope will we need? What do we have to engineer if we've got an angle of repose of 26 degrees and we want a mechanical advantage of 2? And that waffling has given me a chance to type this in the calculator. We need an angle at a slope which is going to be 0.7 degrees. Well, that's just ridiculous, because a 0.7 degree slope to raise us through 1 meter, we need that to be 82 meters long. Well, that's just not feasible. So this actually, this is a nice way to continue on here. This gives us something else from an engineer's point of view. So what if we've got another limitation? We've got this target mechanical advantage of 2, but we're there with a maximum slope of 5 meters. What if that is a limit? We're dragging something up a plank that we've got, but we've only got a 5 meter plank. Now it's a long plank, but that is giving us a limitation here, because that's giving us a minimum value on our angle of the slope. So the most we can reduce theta by is when we've got this setup of 1 meter by 5 meters. So theta min is going to be inverse sine of 1 over 5 of 0.2. So the smallest angle of theta that we can get, this is coming out at, what am I getting, about 11.5 degrees, give or take. So that is a minimum that we're going to get on theta. So if we still want to get a target, we want to hit our target mechanical advantage of 2, and we can't drop theta below 11.5, well, actually, we're going to struggle using this formula, because we're going to have phi's stuck in numerator and denominator here. So let's go for our other mechanical advantage formula and say, okay, well, 2 has to be 1 divided by sine of 11.5 degrees plus mu of cos 11.5 degrees. We can now solve that for mu, and that is going to give us our maximum value. That's going to be mu max. So rearranging all of this, for a maximum coefficient of friction, we're going to get 1 minus 2 times sine 11.5 degrees divided by 2 times the cosine of 11.5 degrees. So the maximum value of mu that we can have is around about 0.3. So you can see how this is different to everything that we've done in a pure physics point of view. We're solving problems from an engineering point of view. We've got a target mechanical advantage of 2. We've got a limitation of a 5 meter plank. That's now given us another limitation on how much friction we can have. We can then turn this into our angle of repose, because we know that is tan of the angle of repose. So we can stick that in. We can say inverse tan of 0.3. We've now got 16.7 degrees. So our maximum angle of repose is 16.7 degrees. So we can see this straight away. If we're going to try and drag this object up the slope, we can put it on the slope, and if it isn't starting to slip before we get the 16.7 degrees, well, we're not going to be able to pull that up the slope. We're not going to get that mechanical advantage. So then we're going to have to engineer the slope. We're going to have to get a different material. We're going to have to put oil on it, or whatever it is, in order to reduce our coefficient of friction, in order to reduce our angle of repose. So classic engineering that we've got going on in here. So there's a lot built into these of problem solving, which is different to our standard pure physics. So yeah, lovely stuff. And this is just the first one of our simple machines. Of course, what I should add here, which I nearly forgot about, is going back to our target here for the mechanical advantage. Okay, I've put in a specific value here of saying our target is 2. But of course, if this is just MA max, we've got this straight relationship here between the coefficient of friction. So looking at this bit here, essentially, this, if I hadn't put in the target, the coefficient of friction has got to be less than 1 over our target mechanical advantage. So there's a direct relationship here between mechanical advantage and the coefficient of friction on this inclined plane. So this is giving us even more insight, as we pick away at this relationship that we identified on the previous set of slides. These relationships up here for mechanical advantage, well, unpick that a little bit more and we get a result here for our maximum coefficient of friction. So we're going to have to keep that in mind whenever you're using an inclined plane, that we have limitations there. So yeah, this adds even more depth to what we're looking at.